introduction to our center. And we are still a little bit before time, thankfully. So we have a few minutes till our speakers can adjust their slides and set up their things. So in the meanwhile, I'll hand over the floor to Nelly, who is our chairperson for the day, and she can take over the working from your end. Thank you, Nelly.
Yes. Yeah, so morning, afternoon, or evening, everyone, depending on which time zone you are in. And it's a pleasure to, of course, chair this opening session. It's also a pleasure, thanks to Sergey, to give us like an introduction to the landscape and things that are happening in IBS. I would look forward very much to visiting it one day. So hopefully I have that opportunity. So let's start. And of course, it's my great pleasure to introduce Sai Vinjanampati. He is from Department of Physics in IIT Bombay, India. And he will be telling us about generalized measures of quantum synchronization. So the stage is yours, Sai. I'm very much looking forward to your talk.
Thank you very much. Thank you, Nelly. Thank you, Juza. Thank you, everyone, for coming to this talk, and thank you very much for giving me the opportunity to speak here today. So I hope that you will be entertained and also be informed a little bit about the stuff that's happening in this little field that I'm here to report to you about. So I'm here to talk to you about quantum synchronization, so this is I think quite apt, because some of what I'll talk to you about will be, a little bit of it will be about thermodynamics, but almost all of it will be about dynamics. And you can clearly see the interplay, which I think goes well with the theme of the workshop. So let me, on the offset, basically tell you that all the details that I'm going to talk to you about are in this specific paper towards the end. So that's the title of the talk. So in case you're interested in following up on details and so on and so forth, you can look for it there. Let me also warn / apologize to you that for those of you who are experts on nonlinear dynamics, I know that several of you are. Perhaps the first part of this talk will be quite basic. Quantum synchronization as a field is basically at the intersection of quantum information theory, quantum thermodynamics, and nonlinear dynamics. And because then the kind of what would you say, the one topic that people are not familiar with is nonlinear dynamics, I typically tend to kind of introduce that a little bit more in detail. So I apologize for that. So with that, let me just begin by just talking to you about what synchronization is. So what is synchronization? Synchronization is the adjustment of rhythms of basically oscillators and with some caveats attached to it. And the caveats, essentially, the devil is in the details. But before I say anything formal about it, let me show you a movie. So this is a YouTube video from Harvard's Natural Sciences. So what this is there are a bunch of metronomes that are on a little platform, and you can see the platform is basically just on the floor. The person who's demonstrating this is going to put it on some cola bottles, and what you'll see is that the metronomes, which are swinging randomly, will start synchronizing. And so you can just visually inspect. I can hear the sound that the thing is making in my ear now, and you can actually see them going in unison, right? So that adjustment of rhythms of self-sustained oscillators is basically what synchronization is all about. Now, why should we care about synchronization in the classical world, right? First of all, in the classical world, why should we care about it? Because in the classical world, actually, synchronization is ubiquitous. So it's all over the place. I refer you to Steven Strogatz's book on this, Pekovsky's book, Balanov's book. There are some very fine textbooks on this topic. But to kind of give you a brief introduction, basically, all kinds of systems which have nonlinear dynamics in them tend to synchronize if you just get some basic conditions right. So where would you find examples of this in nature? So fireflies, which basically blink to signal to their mates, tend to synchronize their blinks to each other. And this has something to do with just short-range interactions, basically. The human eye basically receives feedback, photic feedback from the sun. And so our entire physiology is synchronized to basically the rhythm of the sun. The human heart is actually a collection of cells which oscillates which beats in tandem. And so if the cells of the human heart fall out of synchrony, then you have some form of arrhythmia, which is basically a very dangerous condition. Networks tend to also synchronize. And so the reason that I'm pointing this out to you is that there are small objects and large objects. Many of them are deeply important to us, and they are objects that, at least prima facie, look extremely different from each other, from networks of electricity grids all the way out to the human heart, right? So this is a very exciting field, I must say. Classical mechanics can often be very, very exciting, and this is a very exciting field. And so this is kind of the one of the reasons why synchronization in the classical world became very, very important and interesting. So for this workshop and for this audience, I just want to introduce to you I want to introduce to you essentially two separate things. One is the fact that synchronization appears typically in two separate formats. One of them is called entrainment, and the other is called synchronization per se. And the other is I also want to introduce right off the bat a measure of synchronization, a signature of synchronization. So what do I mean by synchronizing quantum systems or classical systems? What I mean is that I have some sort of phase space here. So you think of it as phase space. So some sort of angle degree of freedom, and you have these phase oscillators which are basically traveling along this circle. So what I'm doing is I'm measuring basically the dynamical degree of freedom that I'm interested in is this angle that they're making, let's say, with some fixed axis. So what you can do is you can either drive each of these, just one of these oscillators with an external drive, just like you would force a pendulum from the outside. And you would basically have a situation where it's a unidirectional coupling. So the forcing term can basically influence the underlying oscillator, but not the other way around. Or you can basically have several of them coupled to each other and have them influence each other. So this is basically the situation which the two situations that I wanted to point out, because they will start making a huge difference as we go downstream into the quantum regime, where I'll basically actually flesh them out in a little bit more detail. In either case, what are you looking for? So when you say that a classical system synchronizes, what are you looking for? So here is the classic diagram. What I'm looking for is at any drive strength epsilon. So this epsilon is either the strength with which I'm coupling these two classical systems, or the strength with which I'm driving from the outside, if it's just a classical laser drive, let's say. At some strength epsilon, what I'm asking is, if I drive at the bare frequency, I of course, at the natural frequency of the oscillator, I of course know the oscillator response. Now, if I keep going off resonance, basically, if I take it off resonance and I create some detuning, what you can show is basically that the dynamics of the oscillator leaves the natural frequency and locks onto the external drive. But it can only do this for a while. Basically, if the detuning is too large, let's say 10%, arbitrarily, I'm just throwing out a number, so 10%, then what happens is that the system is unable to respond anymore because the detuning is too large. And what it does is simply returns back to its natural frequency. So you can draw a boundary by simply identifying what locked is and as opposed to the opposite of that. And that boundary will reveal to you a kind of shape like this, the Arnold tongue as it's typically called. So I'll show you several signatures of synchronization in the quantum regime, where I will basically say this is synchronization because here is an Arnold tongue, right? And so I want you to kind of keep that in mind. Now, the rest of this diagram is quite self-explanatory. All that this is saying is that as you increase the drive strength, this region becomes larger and larger. So at zero drive, then there is basically nowhere for me to synchronize. With a little bit of drive strength, then there is a small region where I see phase locking, and then as I increase the drive strength, then this region also correspondingly increases. So that's what this diagram is trying to tell us. Yeah, so with that little introduction, let me just tell you about the prerequisites for classical synchronization, because this actually becomes, I would say, part of the biggest conversation if you're going into this field here on out. This will become some of the biggest challenges that we'll have to deal with. The first of this is you have to have an underlying nonlinear dynamical system, right? So why do you have to have an underlying nonlinear dynamical system? Because otherwise there is really anything is synchronization otherwise, which is to simply say that if I take a harmonic oscillator and I give it some energy, then it defines a fixed elliptical orbit. And then if I give it a slightly different energy, then that's a valid orbit as well. And these things are not synchronizing systems. It's just linear physics. There's not anything interesting interesting here. So what you want is an underlying nonlinear dynamical system so that you form what's called a limit cycle. And so this is the first thing that you need. The second is that this limit cycle oscillator needs to be self-sustaining. So the simplest way to explain this is basically, this is a diagram that I've paraphrased, I think from Balanoff, I don't remember anymore. And the idea is the following. So let me just tell you what the idea is. So I'm plotting some arbitrary parameter on the x-axis. So let's say it's the radial coordinate. And now what I'm asking is, I'm asking what kind of situation can I have where I form a limit cycle, a stable limit cycle. And the situation is the following. So suppose I'm here in this region, right? So value of R is in this region. Then there is a linear pumping basically, which pumps me up. And the linear pumping amplitude is larger than the nonlinear damping amplitude. And so what happens is the pump takes over and pushes me towards this spot here. Whereas on the other side, the damp is larger than the pump and it pushes me down. So what happens is that on either side of this, you just get pushed back into this, this stable fixed point basically. And so that's an energy balance point here. And at that energy balance point, you basically have an oscillator which can sustain itself. So that's the self-sustained oscillator. So you need that self-sustained oscillator so that you actually are talking about synchronization in exactly the same way that our friends and colleagues in the in classical mechanics understand that phrase, right? And I say this essentially to kind of point at the fact that there is a lot of controversy on what synchronization is even in the quantum community. Now, the third condition I would say is required is that along with the limit cycle, you have to show me that there is a free phase that you can lock onto. This is a point that seldom arises in the classical context, but it'll show up in the quantum context. So excuse the fact that this essentially looks slightly weird here. So here, what do I mean? The moment I basically show you that there is a limit cycle, there is an oscillator there. There's nothing more to discuss in classical mechanics. A la Kuramoto or any other model, there is already an oscillator here, which is going around the ring. The problem is that in the quantum case, the situation is slightly subtle, and let me just highlight that subtlety to you when we get to it. So I want to just end this slide by basically pointing out that these are the three prerequisites for classical synchronization that we need, and I say this basically to just set the tone for quantum synchronization when we go into it. Now, with that, let me ask the following question, which perhaps many of you are asking, which is why bother with quantum mechanics, right? What's the great reason? What is the great desire? What are we as quantum information theorists and people who are interested in quantum technology at various aspects, what are we interested in this stuff for, right? And the answer to this basically came during the time that I was transitioning from my PhD to my first postdoc, so around 2010, where nanomechanical resonators were being cooled to their ground state and demonstrated to be cooled to their ground state. So this is from Keith Schwab's lab. And you can see that, that once we master the capacity to have nanomechanical resonators in the ground state, you really have the capacity to have this interplay between quantum dynamics and classical dynamics. And so this interplay between quantum dynamics and classical dynamics makes for a very exciting study of synchronization in the quantum regime. And this is one of the kind of central reasons. So with that, let me show you a diagram that I have been showing for 5 years now. This was a diagram that I drew with some of my collaborators on a notebook in CQT actually. And so what I imagine is the following, which is, here is a kind of standard cantilever. So it's an experiment that many of us do in high school. And you can also force it from the outside. Now, if you basically apply a magnetic field and you start loading the end of the cantilever with magnetically sensitive quantum systems, then you automatically have an interplay between mechanical degrees of freedom and quantum mechanical degrees of freedom. And you could keep the mechanical entirely classical, and you could keep the quantum mechanical degrees of freedom entirely quantum. And so you have this kind of very interesting mix of dynamics that comes up. And it provides us, I think, with tremendous opportunity to kind of bring the stuff that we know about classical synchronization into the quantum regime. So that's something that I just wanted to show you here. And finally, we're not the first and definitely this is not an original thought. So here is an example from the literature. So this is Kerry Vahala's work from 2009 on basically using the van der Pol oscillator as a phonon laser. Yeah. So should I take questions now, Nelly, or should I just wait for the end?
You are free to take questions if you want to.
Okay, I see a raised hand, so I'm happy to take questions.
Yeah.
Right, thanks. So you mentioned there is entirely classical, entirely quantum. Can you tell us what's the difference in your mind? What's the quantumness about it?
Oh, yeah. So you can quantify it in many different ways. So typically, the kind of uncontroversial way that people would talk about it is action over h bar. So you would say, are you close to the ground state or are you very far away from the ground state? So this is the practical way in which people have talked about it in the literature. So if the average number expectation value of, let's say, a harmonic mode, which I'll show you, has hundreds of photons in it or dozens of photons in it, then perhaps we're not in the classical regime, in the quantum regime anymore, or at least we have to have a discussion about. Right? This is one way to do it. Another way to do it is basically to check whether the mean field dynamics actually is in agreement with the full classical dynamics, or sorry, the quantum dynamics. It is sufficient to describe by simply looking at the classical dynamics, the mean field dynamics, or if you need more moments. So there are many ways to kind of, and as I show you some diagrams, this will also become very clear. Yeah, thank you very much. Okay, any other questions?
Yeah, I have a question. So,
yeah,
can you hear me? So, what do you mean by classical forcing of a quantum system? Because force is not a well-defined concept in quantum mechanics, right?
Oh, I just mean exactly this experiment. This is motivation. So take it for what it's worth. All I mean is just this kind of a thing, which is let's say I have an anisotropic magnetic field. So depending on where I am, the qubit degree of freedom or the qubit degree of freedom that's at the end of the cantilever is seeing a different force. And now I just couple it to basically just a classical resonator. So this thing has hundreds of phonons in it, whatever, but kind of the separation is such that, and the gradient of the magnetic field is such that I need to worry only about the extreme ends, right? And it's just, you can design these kinds of. So this guy is completely classical, whereas these qubits may be, maybe embedded, but be at a frequency where you don't care about the temperature that you're operating in.
I see. Okay. Thank you.
Yeah. It's just Okay. Very good. So with that, let me move on to the first kind of quantum part of this conversation, which is quantum synchronization. A la anharmonic oscillators, right? So what I want to do is I want to transition all of us from classical synchronization over to quantum, and just share with you how we would do this in the quantum context. So this is a classic example. So one of the kind of prototypical examples of synchronization of the classical regime is to just study the van der Pol oscillator. So let me just explain to all of us what the van der Pol oscillator is. So it's just a harmonic oscillator, so x double dot plus omega square x, and then there is just a linear pumping term, a minus gamma 1 x dot, and then a nonlinear damping term. And I've explained to you why you need this linear pumping and nonlinear damping. It's because you need that energy balance so that you get a stable fixed point, right? And now you can also force it from here, right? So just to kind of give you a pH 101 kind of picture, here is a diagram of what the dynamics looks like if I just set gamma 1 equals gamma 2 equals some constant, which I've just called mu in these plots that I've made. And what you can see is that when mu is small, which means that the inherent nonlinearity that you're applying is quite small, this thing looks quasi-harmonic. It basically looks like a harmonic oscillator, but it's doing something funny. And what it's doing is that wherever you set it up, it just rolls into this limit cycle. You can see there are tens of limits. There are tens of oscillations here. You can count them here exactly. There may be 4 or 5 oscillations here, where it takes time to roll into the limit cycle, right? And as you increase the nonlinearity, the limit cycle becomes more and more deformed, which is interesting for a different set of context, which I won't get into here. Yeah. So this is what the phase-space dynamics looks like, and I just wanted to share that with you. And along with that, I just wanted to share with you what I mean by phase localization, right? So in this context, what do I mean by phase localization? So you can see that there are these things that are moving around in a circle. So the quasi-harmonic example, you can just take mu equals 0.1, and I can set several of them up, and I can set them up in such a way that if I track the particles, they could essentially be on a circle. And now I could couple them and ask whether they get closer to each other, and hence their rhythms adjust and they start synchronizing their oscillations to each other, or are they doing something different, right? So I could ask these kinds of questions, and so that's what I mean. So I mean that phase degree of freedom that you've just seen, I want to kind of try and lock it either to an external drive or lock several of them to each other. Yeah. Okay. So from master equations to quantum synchronization. So how do I go basically from quantum mechanics to this kind of a picture? So this was done by Walther, Noonan, Kemp, and Bruder in PRL in 2014, and Lee and Sadehpur shortly thereafter. So the way to do this is the following. Walther, Bruder, and Noonan, Kemp did was they pointed out that if you start with a master equation of the following type, where basically you have a Lindbladian superoperator which represents linear pumping. So this is exactly the analog of the classical version that you saw, and a nonlinear damp as well, the analog of the nonlinear damping that you saw before. And the Hamiltonian is basically some detuning times the number operator and f times y operator. So y is basically a minus a dagger. Then basically, if you just calculate what the equation of motion for the expectation value of the annihilation operator is, so this is this complex number beta, which is just defined as trace of a rho, then the beta dot equation essentially is some cousin of the van der Pol oscillator. So it's what's called the Stewart Lambda oscillator. And so what they pointed out, what Walther, Bruder, and Noonan pointed out is basically that you could arrive at the classical equation for a Stewart Lambda oscillator by starting from a quantum mechanical system where the dissipators had a nonlinearity inside it, right? And so that's interesting. And then they basically plotted diagrams like this. So I just want to explain this diagram to you because this also answers one of the questions that was asked about what's classical, what's quantum, how do I think about it? So here are two regimes, one basically where the action over h bar is very large and the other where the action over h bar is very small. When the action over h bar is very large, what's plotted here is the Wigner function. So this is the normalized momentum expectation value and position expectation value, and for the classical oscillator. And on top of it, basically, is superposed the normalized Wigner function. So both of them are sitting right on top of each other. And so the black line is the classical dynamics that you would expect if you just picked some parameters, gamma 1, gamma 2, delta, and f, the amplitude and phase of f, and you just plotted this, you would expect some circle like this. And this is just a limit cycle oscillator. And now what they showed was that the Wigner function sits right on top of it, perhaps as we should expect. Now, on the other hand, when you basically take the small action over h bar limit, when you go into the deep quantum regime, then what happens is that the classical limit cycle dynamics is sitting over here, whereas the quantum is a little bit more smeared out, basically because of the uncertainty principle. And so this kind of diagram they showed and to kind of convince the reader that there is synchronization just as we understand it in the quantum case. So there is phase localization in this case. So the way to think about this is that instead of thinking about this in position and momentum space, you could also think of it in terms of number and phase operators. And if you think of it as the phase operator is completely delocalized over here, whereas the phase operator has a localized value over here, which tracks basically the conversation from the classical dynamics. So this is basically the point that they were trying to make. Okay, so I already want to highlight.
Sorry, sir. Can I just ask you a question? I'm a bit puzzled. So yes. the black loop is the classical solution, right? It's a limit cycle.
Yes.
How can it be that so normally on a limit side, if you have an oscillator, then momentum should always change sign, but this doesn't seem to be the case in figure B. So the black loop is always sitting at negative p's.
So I can look at the exact paper to tell you exactly what's happening. So I believe what they did here was basically they were just trying to establish that there is a limit cycle, and in the large action over h bar, you actually do expect to see what you see in the classical regime. In the quantum and the classical agree with each other. Whereas here, I think they were trying to turn down the quantum dynamics, but also they were doing something to the to this f. So so the classical version of this f. So, but I don't remember the details anymore. Yeah.
Thank you.
Yeah. Okay.
Sorry, Sai. Quick question again about this panel B that you show here. So, for synchronization, you need a limit cycle, right? But in this, what you call as a deep quantum regime,
yes,
I don't really see a limit cycle type of behavior. It's more like a localization behavior.
No, I think this is already driven. This is already the driven dynamics that you're looking at.
I see.
Because you look at the quantum and you can see there's phase localization already. So they're not trying to show you the limit cycle underneath. They're just directly showing you the localization, I believe.
Okay. Thank you.
Okay. Yeah. Any more questions? Yeah.
Yeah, so I wonder, maybe you will talk about later, but you mentioned a couple of times like a phase operator and measuring phases. So phase is not an observable in quantum physics, right? It's a parameter. You can make it you can make something like an observable, which is some kind of unbounded operator, but it's really not an observable. So I wonder, you know, because you talk about synchronization, but
So this is
systems.
Yes. So they mentioned two things, two separate things in the paper. One is that you can define basically, you can take the Wigner function and you can integrate out the radial coordinate, and you can define a normalized probability distribution which only belongs in the phase degree of freedom. And that's what their plot, they show you the plots of that to convince you that there is phase localization. So in that technical sense, they're basically talking about phase localization.
Oh, I see.
But no notion of, let's say, Peg and Barnett phase operators or anything is used to, no unbounded phase operators are actually used to measure synchronization in the quantum regime. So in the quantum regime, as I will show you in a second, what they use is several measures, all of which are well-defined. They are either depending on power spectrum, or they depend on basically this kind of Wigner function-based measures and so on and so forth, which are perfectly well-defined. Yeah.
Okay.
Yeah. Okay. More questions? Okay. So let me just summarize again, because this is an important point, which is I've already snuck in through this conversation the point that Walter Brood and Untitled make in their paper, which is that they're measuring quantum synchronization using a phase space-based measure. So they're looking in phase space and they're saying something about what phase space looks like to basically make their argument about synchronization. So this is something that I just want to highlight, because this also becomes important. Okay, so with that, let me just quickly introduce what phase space-based measures of synchronization, how you would construct them. So phase space-based measures, you know, so there are many phase space measures in quantum optics. So here is the Husimi Q representation function. And the Husimi Q representation function you can think of as being derived from the Wigner function, or you can think of the Wigner as being derived from the Husimi. And I wanted to highlight both of these at the same place, because the Husimi to me is much easier to define. It's just the expectation value of the coherent state. And the Wigner, on the other hand, is the one that was used by Walter Brood and Untitled. So you can make an association between these two by simply just this integral transform. And what I just also want to highlight is something that all of us know, which is basically that both any phase space quasi probability distribution, the Husimi Q representation, the Wigner function, all of them are basically one-to-one with the density matrix. So it is as if I'm just giving you the density matrix directly when I give you the phase space measure. And so a measure of synchronization which is based on a phase space quasi probability distribution is as if you're just calculating it directly out of the density matrix. So this is just something I just want to make very clear. And you know, and here is just a picture of one of these Q representation functions for squeeze states. Yeah. Okay, so with that, let me also point a little bit at the other measures that were used. So one measure that was implicitly already there, and it's made more explicit in the paper, is this phase space-based measure of synchronization. Yes, Nelly, did you have a question?
Yes, can I quickly interject, because there's a question in the chat
asked yes.
For the slides above. So when we were talking about the master equation and the dissipator,
sure.
The question is asked by Ricardo Ancheta, basically asking about whether the nonlinearity is only in the dissipator but not in the Hamiltonian.
There are many examples where they've been put all over the place. So there are dissipative. So you have to have dissipative nonlinearity. This is a must, because otherwise, what you don't have the analog of the stable limit cycle. But if you have basically dissipative nonlinearity, people have also kind of put all kinds of nonlinearities in the Hamiltonian structure, and there are some papers on this as well, which I can point out. In fact, many of the analog examples of few level atoms that I'll show, everything is nonlinear. Like every single term in the thing is nonlinear. Yeah, so that's okay. So I didn't need these slides after all.
Okay. I also see a raised hand by Taufik Murtado.
Yes.
Yes. So I have a question about, you said it's one-to-one between the Hishimi function and the density matrix.
Yes.
But as far as I learned, because in phase space representation, it's actually like continuous. But you know, in quantum mechanics, the degree of freedoms is kind of discrete. So I wonder how can it be one-to-one?
Oh, no, no. So there are two distinctions in kind of there is essentially two classes of quantum mechanical problems that we study. So when we begin basically perhaps our bachelor's or master's quantum mechanics, we're usually introduced to kind of square well potentials, infinite square wells, so on and so forth, hydrogen atom. All of these are continuous variable degrees of freedom. There's an infinite set of modes there. And so the simpler way to handle them is through function space, through differential equations and function space. But then there is a separate set, which is basically, there's a separate way of doing linear algebra just for finite dimensional matrices, which is a much simpler object that we deal with on the side. So so this question is actually very, very important topic. So I thank you for bringing it up. So the point really here is that even though what I'm saying here is for the same Hilbert space dimensionality. So if I have a harmonic oscillator, whether I give you the density matrix for it or I give you the Q function or the W, it's the same. This statement is true everywhere as well. So when I go to spins, the real question that you should ask is how do you define coherent states with spins? And once I show you how to define coherent states with spins, the Q function will also basically have only a few parameters. And so you will be able to capture everything about a finite dimensional Hilbert space, basically. Yeah.
But yeah, wouldn't it be like over complete kind of thing?
They're all over complete, yeah, but that's
Yeah.
by design, so that the diagonal distribution already tells you everything that you need to know. Yeah.
Okay. Thank you.
Good. Okay. Thank you very much. Okay. So with that, let me just introduce to you just a couple of more measures of quantum synchronization, because this is, of course, the whole talk is about the measures per se. So here is another measure of quantum synchronization, again from Walter Bruder-Nunenkemp's paper. And so what they're looking at is basically the power spectrum that comes out of the system. So this is the Fourier transform of this quantity. And the only thing I just want you to take away from here is the following, which is that here is where the classical drive frequency is. It's implied by basically these delta function peaks. And then the quantum dynamics, basically the Fourier transform is plotted right on top of it. And you can see the peak is kind of proximate to where the classical blue peak is, right? And then there are these other values of the parameters for which basically, so the detuning is basically 0.5 versus 0.7. Where basically there is somewhat of a large deviation, and they make commentary on this and so on. This is not very important for our purposes, but the central point I just want you to take away from this slide is basically the power spectrum can also be used. So you could basically just take a very operational approach. You could just say, I know synchronization is oscillation, and my oscillating atoms will emit. So I just look at the power spectrum. I just stand back at a distance. I stare at what the emission that is coming out. And the peak of the emission I identify as basically being the observed frequency. And by using this as well, they were able to show that you can plot essentially an Arnold-Tung. And so this measure also follows the Arnold-Tung description. Okay. Okay, and with that, let me just show you the first Arnold-Tung in the whole story. So this was a paper by Ameri and Sarofatsios on this paper. And so what they were saying is the following. They said, look, what are we really trying to study? Let's think about it again from our perspective. And this was around the time when people were thinking about entanglement or discord or complicated measures of synchronization, basically. And somewhat motivated from the entanglement school of study. And so what Ameri and others basically were saying was, they said, look, it makes no sense for us to study a phenomenon like synchronization, which exists in the classical world, by constructing a measure that will completely fall apart in the classical world. So let's say if you create an entanglement measure will register 0 whenever you hit the classical world. So the moment I hit a classical boundary, if I register 0, then I'm actually doing a disservice to the field that I'm trying to study. And so here is the cartoon here, which is, 2 metronomes. I just showed you the video of several metronomes. I can study them. I can study the synchronization, the classical synchronization of 2 metronomes. And if I just happen to keep cooling them, then I get into this weird regime that we're interested in, right? So their proposal was basically, they said, so here is the system that they were considering. So there were 2 cavities with qubits in each cavity coupled to each other. So it's a slightly complicated system. But what they were basically saying was, they were saying, let's study the mutual information between the two systems, right? And so this is really the only point that I want you to take away, which is mutual information actually is a well-defined information theoretic quantity that is well-defined both for Shannon entropy type quantities and von Neumann entropy type quantities. So it can go through kind of the classical quantum transition along with your quantum system. So if you take basically one of these, this kind of a cartoon example of these two metronomes, and you just pour liquid nitrogen or cool the whole thing down, as you are performing the transition, your mutual information measure could actually follow you, basically, just quite nicely into the quantum regime and follow you back up into the classical regime. So their proposal was, let's study mutual information as a measure, right? And so this is something also that I want you to just take away with you. Okay. So in all of these, I just want to highlight to you. So what I've shown you thus far till now is basically several examples of measures of synchronization. And so now I'm going to go into the few atom regime and also just expand this whole conversation before I show you our solution. Before I kind of get carried away, I just wanted to again highlight to you what angles am I talking about. I'm talking about this particular angle, right? I'm talking about the fact that if I just have a harmonic oscillator mode, nothing attached to it, nothing. So the number operator basically is the operator. So the states are number states and they're phase invariant. And now if I basically drive them, then they start driving along this direction. And so the phase locking is, I'm interested in that direction, right? So think of it very visually, right? Which is I have a pendulum and it basically, if I do nothing, it's just moving in this direction. That's the degree of freedom I want to lock to. So that's the physical degree of freedom that I want to lock to. And so this conversation also becomes very important as we go along. So this is why this cartoon is here. Bhavish, I am happy to take a question.
Hi. So I just wanted to ask, in the previous slide that you showed that they study quantum information for the metronome experiment. So what would be the states of the metronome here? And like
the metronome is a cartoon, Bhavish. Sorry, I'm sorry for the confusing imagery. The actual quantum system is actually I don't know if it is invalid is the phrase to use, but it's controversial. So I just want to leave it out of the discussion.
So the system is something different.
But the system is two cavities, right? So you can see that there is AI going from 1 to 2, and each cavity has like some qubits inside it, and you want to study whether the qubits are synchronizing to each other, because the cavities can talk to each other. They're leaky cavities that can talk to each other, basically.
Right. Okay. That makes more sense.
Yeah.
So, okay. Thanks a lot.
Yeah. But if you were to study metronomes, Bhavish, literally you would just use one of these anharmonic van der Pol oscillator master equations that were defined before. Yeah. So you could actually, I could answer the question that you were directly asking. It just happens to be not the one on the slide.
Okay. Thanks a lot.
Okay. Thank you very much. So again, just to emphasize, to just underline this slide. So which angle? So what you have to do is you have to look at what the free dynamics is, and the free dynamics just simply puts you in this direction. So you switch off F and you ask what's happening. It creates these kinds of concentric rings, which I can think of as phase invariant states. And then what you want to do is you want to ask what happens if I switch on a drive. The drive actually it's an operator that takes me along this direction, right? Because of the dA dagger and dA square, I'm stuck along this limit cycle. And so what the drive does is it actually can manipulate this free phase degree of freedom, and so that's the direction in which we would want to lock. Okay. So with that, let me just give you one of the only two side notes in this entire conversation. So we took this problem. So the power spectrum that I showed you, there are some issues with the power spectrum with respect to basically its observability in the deep quantum regime. So we worked on a solution on how basically a squeezing operator applied to this basically can help you with the whole story. I won't say anything more than this, and this is in a paper from a couple of years ago, which I just highlight. Okay, so with that, let me move on to the next stage of the talk, which is about n-level atoms. And what I'm going to show you towards the end is how to combine all of these into one information theoretic measure. This is where I'm going. Okay, so again, the question is, how do I discuss synchronizing n-level atoms? So let's say 2-level atoms, 3-level atoms, 4-level atoms. I want to now have this conversation not for harmonic modes or anharmonic modes, but I want to have this for kind of finite level systems. So this was the question again that Bruder was asking. And so let's again recap. Synchronization of classical systems requires an existence of a limit cycle, and these angular coordinates should then exhibit locking if you phase lock them, right? So So this is a classic example. If you want to look at it in the radial direction, this is just a stable limit cycle. I've just written it out, the differential equations for it, if you want to look at it. So what Bruder asked, Roulet and Bruder asked, Alex Roulet, who was at CQT, what Roulet and Bruder asked was, they said, well, does this preclude qubits, right? And so does the existence of a limit cycle preclude qubits? And of course, they're asking this question, so the answer is yes. The argument is the following. I just want to present the argument to you. The argument is basically, they said, well, take a limit cycle for a single qubit density matrix, right? What is a limit cycle? A limit cycle is one where at least one phase degree of freedom is left open, right? So qubits are expressed on the Bloch sphere, so they're states on the Bloch sphere. So they have a radial degree of freedom, which is irrelevant to the discussion, and then there are two angles, theta and phi. So so let's try and fix basically the population, so that we fix basically the amount of admixture between 0 and 1. So when I fix the population, so let's say P and P bar I fix, what do? I'm basically fixing the theta degree of freedom. I'm fixing cos square theta over 2, sine square theta over 2, right? And then I have a phi degree of freedom that I can then think about locking onto, right? Exactly the same as all the other limit cycles. So what they showed was basically, so this is the argument that I've just presented. What they basically pointed out, essentially, the argument is trivial entirely, is that if you multiply 1 by e to the minus I phi times 1, it just goes away. It's a gauge degree of freedom. So it's an unobservable phase, basically. So even though you have a limit cycle, mathematically, you don't actually you can't see it. It's not an observable limit cycle. And so they basically precluded qubit synchronization. And this is something that I just want to highlight, because depending on how much we bring from classical mechanics into this quantum world that we're in right now, the definition of synchronizations change. So you could disagree with me in the Q&A, and you can say, here is a paper that I have read and which says that qubits can be synchronized. And I'm happy to make this discussion with you. All of those examples are the ones where they're ignoring one of these statements. And so I think the community as a whole, as we go forward, will have to decide which of these comments are basically the important ones and which are the unimportant ones. And so I just want to maintain to you that so long as I'm concerned, and so long as I think Bruder's paper is concerned, qubits cannot be synchronized. Okay. So the smallest quantum system that you can indeed consider is a spin 1 atom. Right, so it's a 3-level system. So what Roulet and Bruder did was the following: is they said, okay, so why don't we take basically a 3-level atom, but a symmetric 3-level atom, so an equally spaced 3-level atom. So the two energy level spacings are the same; they're omega naught. And then what I do is I pump from below and I damp from above. And so when I just leave the system alone, it just settles in the middle state, right? So the middle state is observable, and I'll show you that it also corresponds to a free degree of freedom, a free phase, right? So this is basically the whole point. Now, how do I do this? The way I have to do it is I have to follow classical mechanics. Yeah, Matthew, you had a question?
Hi, I was just wondering about the 2 slides ago about the 2018 PRL. So you were showing that because the phase doesn't manifest in the populations, then you don't get the limit cycle. But what if you had coherences, or maybe if you coupled your qubits to an open bath, so that you can actually vary the R of the Bloch sphere?
So the moment you basically have coherences, you already are phase localized in the degree of freedom that you're trying to lock. So remember what you have to have when you have classical mechanical oscillators that you're trying to synchronize. You have to have many oscillators, and if you leave them alone, if you don't touch them, they should just be running around, right, like runners on a circle. And when you couple them, basically, then they basically adjust their rhythms to come together, to go apart, to do whatever, to do the various complexities that we know in classical mechanics. The problem here is that the only way for you to observe, basically, that there are runners available is to actually lock them, which Bruder argues precludes it from actually being a valid limit cycle, because it's not an observable limit cycle. That's the whole argument.
Okay. Thanks.
Okay, so I have 15-ish minutes more, so let me speed up a little bit. So So now what I want to do is basically I want to point out to you how to synchronize spins, right? So how do you discuss phase localization in spins? What is the free phase? This is again the question that you have to ask. So what did we do for harmonic modes? What we did was we took the displacement operator and applied it on the quantum vacuum, and we defined a coherent state. And then we took the expectation value with respect to the steady state of the master equation, and that's how we defined the Husimi-Q representation function, right? Normalized. So you do the exact same thing for spins as well. So spins also have a spin coherent state that you can define, but because spins are basically bounded both from below and above, you can define the coherent state either pegged to the bottom or pegged to the top. And so one of the canonical representations I've just written out mathematically for you here is this representation. And so you take this n, this coherent state, and you can define basically a Q function, a Husimi-Q representation function for n level atoms, basically. So this is as simple as it goes. And now when you plot this object for the n level atoms, you can show that there is actually a free phase. So let me show that to you. So for Roulet and Bruder, what they basically showed was that the relevant object is basically called N2. So it's the SU2 subgroup of SU3 if you're interested in a slightly technical detail. It has two angles, this theta and phi. And what they basically pointed out was that in this coherent state, if you apply the free Hamiltonian, then the phi degree of freedom basically moves, but the theta degree of freedom doesn't move. So it's as if you have a pendulum and the pendulum is rocking along this direction, but the length is not changing. So the length is an irrelevant degree of freedom and you can just integrate it out. So what you can then do is you can basically plot the Husimi-Q representation function, and you can in fact show that corresponding to this 1-0 state, there is actually an entire band which has an angle which is completely free. So in the equatorial plane, you could be anywhere, it's observable, but it's not locked basically. So that's the whole point of view that they took on this. And then what they basically showed was that using this, you can construct a synchronization measure. And the way you construct a synchronization measure is you take out the degree of freedom that you're not interested in. So let me again remind you, there are two angles here, theta and phi. Theta essentially represents the probabilities of the three-level atom. So how much probability is there in the -1, how much is in the 0, and how much is in the +1. So by integrating that out, you actually get the phase dynamics of the atom, and the corresponding synchronization measure S of phi is constructed by making these arguments. So this is the underlying construction. Okay, again, all I want to highlight to you is basically that this construction is a little bit tedious. It involves recognizing the corresponding SUN coherent states, and then constructing the Q function, integrating out. This is a slightly messy procedure. So let me just quickly flash that we did the same thing for an engine application. So to study kind of Scoville-Schulz-Dubois thermal engines, basically, we studied the same thing, but in the full SU3. And so the full SU3 has a few more angles. So you can recognize the Q function, again, an expectation value of the steady state in the corresponding coherent state. The coherent state just has more description attached to it. And then you have to take out some unit part, which basically represents the identity, and you get a synchronization measure. The only thing I want you to take away from this is more angles, more integration. This is the only thing that I just wanted to walk away with. Okay. So just as a side note, we showed that there is an Arnold tongue that you can see. And the other thing that we also showed was that this Arnold tongue can be understood in terms of an L1 norm of coherence measure. This is important because I'm going to flash again the L1 norm of coherence in about 5 minutes time. Okay. And there's some engine related statements here, which I thought I could make if there was time, but let me just move past it. Okay, so let me highlight to you the issues with existing measures. The first issue is basically that the power spectrum based methods are very tedious. You actually have to calculate the power spectrum over the entire frequency domain, so on and so forth. And this is actually a computationally even tedious task. The second is that the phase space based measures have too many angles, right? So the number of angles goes as 2 times n minus 1. And so the total number of angles basically proliferates. And so this integration procedure, so if you were to study a 10 level atom, you'd just be there all day basically doing this calculation. The third is that the mutual information ignores any details about the marginals, as I'll show you in a second. So the mutual information is in fact probably the closest to a very good definition that we like. The fourth problem that we have is that we cannot really synchronize dissimilar systems with these techniques that are there before. And what we're really interested in is Jaynes-Cummings type problems, basically atoms inside cavities that are coupled to each other and we drive the whole thing. And we want to study synchronization, not just Jaynes-Cummings dynamics here. The fifth is basically that entrainment and synchronization have to be treated essentially on completely separate platforms. So entrainment has to be studied as external driving, blah, blah, blah. Synchronization has to be studied essentially on, in a different method altogether. And so they're not treated on an equal footing, which we also fix with our measure. And the very last thing is something that I will begin my next part of the talk with, which is deformation of limit cycles is completely ignored in the perturbative study of synchronization. So till now, all of the synchronization studies that I've shown you are basically in the perturbative regime. And so in the perturbative regime, you're not supposed to deform the limit cycle. And because of this, people have actually ignored the fact that the limit cycles are very easily deformed, especially in the quantum context, with a little bit of power. Okay, so with that, let me just quickly come to the end of my talk, the last 10 minutes or so, with this unified measure, which is the substance of my of the current paper that I want to highlight to you. And so let me highlight to you what the story is by just showing you this cartoon. So suppose I have an undriven van der Pol oscillator. So you can see my cursor. So the classical limit cycle is there, and the Wigner function is surrounding it. Now what I do is I just kick it. I drive it by applying some force on it. What it does is unknown to me. It heats the quantum system. It does something to the quantum system which deforms the underlying limit cycle, right? So the limit cycle actually goes over there. And now what happens is that my quantum system is phase localized. I see that it's phase localized, but when I try and account for it, I'm getting the wrong numbers. And why do I get the wrong accountancy from it? Because this deformation has not been taken into account. No measures of synchronization that exist till now take into account the fact that you can deform the limit cycle and then phase lock around it. And so we wanted to fix that. And so what we did was we proposed a unified measure of synchronization. So this was in my cartoon in the title slide, which is basically, it's just a KL divergence relative entropy discussion. So we proposed two measures of synchronization. One is the relative entropy of synchronization, which is minimizing the relative entropy of the given state to a set of limit cycle states. So really what we're doing is we're borrowing the language from quantum information theory. And we're saying, look, there is not one limit cycle there. For a given dynamics, for a given damping rate, there is one dynamics, but one limit cycle. But from an information theoretic point of view, there is actually many, many limit cycles there. And because you could change the limit cycle by actually doing something to the quantum system as well, you want to take that into account by using this modified definition, which accounts for a set of limit cycles. And if you minimize the relative entropy, you just get the relative entropy of synchronization. Whereas if you minimize the trace distance, you get the trace distance measure of synchronization, right? So this is a very simple mathematical statement that I can write. And so I just highlighted to you in pictures again. So what I'm basically saying in pictures is I don't take this dotted line, which is the original limit cycle underneath. I take perhaps this outer line that I have drawn, which is basically the true limit cycle. If I turned off the coherent interaction, which would delocalize the quantum system, but left the new damping alone in there. And so my coherent drive is coming with some damping. And so, so that's the kind of logic attached to this conversation. Okay, and so what are the issues here? The issues here are basically that the set of limit cycle states, sigma, determines basically all of the discussion from here on out. It dictates the measure. So an example of this is this deformed limit cycle set that I've just mentioned to you. It also allows us to consider on one footing basically both unipartite and bipartite limit cycles. There's no problem whatsoever. Unipartite and bipartite are simply subsystem statements, and they're not particularly difficult to make. Also, it allows us to take into account marginal limit cycle states, as I will show you. And it also allows us to discuss coupled, dissimilar coupled systems, which is, I think, a great hope, basically, for us to make interesting synchronization discussions in the future, right? And the final condition, consistency condition that we always impose on ourselves in quantum information theory is that it has to match with existing measures wherever they exist. So all existing measures have to kind of lock, we have to lock onto and show that they work so that, we have consistency checks. Okay, so with that, let me just show you very quickly. Again, there's not much math that I'm presenting now. I'm just going to give you the heuristic argument. Let me present to you how basically the different measures go. So let's say that I have a unipartite system, right? So one quantum system, and I'm just driving it from the outside with a classical drive. So this is all that I'm discussing. I have a limit cycle which basically I define as a diagonal set of states. So some probabilities qi times some states ej. Right, and so what I can then do is I can compose what the relative entropy of synchronization is. It's so the relative entropy with respect to the limit cycle set rho lim. You can show, this is just 2 lines of algebra. You can show is the relative entropy of coherence plus the Kullback-Leibler divergence, and of course the relative entropy of coherence is defined here. It's the difference between the diagonal and the full density matrix, von Neumann entropy of the density matrix. And of course, the central point here is that if you minimize Kullback-Leibler divergence, the minimum is found when p equals q. So it just drops out. So what you recover is a statement that we had proven in a paper with collaborators before in this paper by Naufel and others, which was that the relative entropy of synchronization is nothing but the relative entropy of coherence, basically. And so our measure basically captures one of the results that we had derived in a previous paper. Likewise, what you can also show, instead if you compute the trace distance measure, is you can also show that the trace distance is upper bounded by the L1 norm of coherence, which is another statement that we had proven in the previous paper. So these connect to basically well-known information theoretic results from other papers. Okay, so let me also show you, this is a trivial calculation, a 2-line calculation, basically, well, a 1-line calculation, which is if I take the relative entropy with respect to the limit cycle set, which is the marginal limit cycle set. So if I say my underlying limit cycle, I define as the set of states that I get when I just take the marginal distribution, then basically I just get the mutual information measure. So the mutual information measure, which you had seen before, is simply a special case of this more general definition that we've constructed. And so in that as well, we make contact with all of the existing measures before. One more set of examples that I want to give you, which is if I basically have a bipartite quantum system, so this is not unipartite now, I have a bipartite quantum system and I want to calculate the relative entropy to the diagonal distribution. So I say that when I don't drive, this is entirely diagonal. Then what I get is the relative entropy of coherence, so the well-known norm. But there is a small addition of basically the classical mutual information. If I say that I have 2 engines which I'm talking about, and when I don't couple them, the 2 engines actually don't talk to each other. So my diagonal limit cycle set is not a joint diagonal limit cycle set, it's actually delta A tensor delta B. If I have a tensor product structure underneath, which basically makes physical sense, if you have uncoupled quantum systems that you then couple, then maybe this is the one that you would want to use. And if you use this one, then basically there is an additional classical mutual information theoretic contribution basically to the relative entropy of coherence, which we proved basically. Okay. The last example that I want to show you is a slightly is a kind of complex one. So imagine that I have 2 engines or some applications that I'm discussing where I have a 3-level atom, but this is already being driven across 2 levels, right? So this is also being driven. So it's a non-equilibrium steady state basically because of some coherent dynamics. It's already sitting there. Now what I want to do is I want to couple them and I want to study synchronization. I want to play the same game as before. I demand this. Now I ask you, how do you do this, right? And our answer basically was the following. We said, okay, so how does the underlying limit cycle look like? Before I applied the yellow coupling, the underlying limit cycle was basically this top level was whatever level it was. And then I have some coherences in the other 2 levels, right? So the 3 2 levels are basically, there's some coherence there. And so what we did was we basically started with a diagonal distribution and we applied a unitary operator, which was basically just a rotation in a subspace, right? And by constructing that set of limit cycle states, now, so this sigma is now a set of limit cycle states if I vary over all small u. And the u, I'm just giving you the representation of it, the Euler angle representation of it. We were basically able to construct an analytic formula. It's in the paper. It's a slightly tedious formula. An analytic formula for exactly how to calculate the synchronization measure for this kind of a system. So partially coherent dynamics. Okay. And with that, let me just, I think, get to the last example before I conclude, which is what if I wanted to do a completely dissimilar system? So we wanted to show off that we could do something really crazy. So what we did was we basically started off with a van der Pol oscillator, so which was the first part of the talk, if you remember, a quantum van der Pol oscillator. a 3-level atom, which was the second part of the talk, and we coupled the both of them. So it's just a completely weird system that we've just coupled. Don't ask me how to make one. This is just a mathematical exercise as of now, right? More physical examples will follow if you want me to talk about them. And so what we did was each of those is basically a nonlinear oscillator with well-established limit cycles, so on and so forth. And what we were able to do is we were able to actually construct the underlying measure. And if you plot it, you can see a normal tongue. And so this is proof that indeed you can discuss the synchronization of completely dissimilar systems. A nonlinear van der Pol oscillator, infinite dimensional harmonic mode coupled to a 3-level atom, which is also another nonlinear oscillator, right? And so this is the exciting thing about it. And why would I be interested in this? So this is a diagram that I had made for a different paper, but I borrow it because it just makes the point, which is if I could imagine that I have many atoms sitting inside a cavity, and the atoms have some internal structure which is desirable for whatever purposes, and I drive it from the outside. And by making the drive field nonlinear, by attributing some quantumness to the drive field and then making that drive field exciting, interesting in some ways, we could actually see synchronization dynamics in cavities that we've never seen before. And this would actually open up a huge class of other applications which we're working on, which I think is very exciting. Okay, so with that, I'm just at the 1 hour mark. So let me present my conclusions. I thank you very much for your questions and your patience. So what we've presented here is basically a small discussion on quantum synchronization, which follows from the classical synchronization, what we understand from classical synchronization. So existing measures are very important lessons, but they're difficult to compute and they have small limitations, which I have highlighted as far as I could. So what we have presented here for you is a unified measure of quantum synchronization that reduces to all the known examples. So it's actually a good measure that captures all the stuff that we've known before. And furthermore, it's easy to compute. There are tons of closed form formulas already in the paper that I urge you to kind of look at and also deploy. I think the favorite selling point for me is simply the fact that it's applicable to extremely dissimilar systems. So we can actually now go after synchronization, which is in the real world, atoms and cavities and so on and so forth, which I think is very exciting. Okay, so with that, let me just thank my collaborators in my group. So Parvinder, Solanki, and Naufal are basically on this paper, and they've been working with me. Naufal is just about to leave us. And of course, Samir was at an earlier paper. He's an undergraduate who's now moved on. And my collaborators, Mikhail, who many of you know, Professor Sarafazio, and Professor Kwek, who are both long-term collaborators of mine. Okay, so I thank you very much, and I'm happy to take questions. So here are some papers that basically directly refer to our work.
Thanks very much, Sai, for the great talk.
Thank you.
I think we are more or less at the time, like there were already a couple of questions very nicely woven into the talk, but is there any remaining questions still from the audience? So I see still two maybe remaining questions in the chat, and one is about how nonlinear dissipators are realized in experiments. So if you know some quick examples to give them.
So one of the famous ones is basically in Lee and Sadehpur, and following them several people, including we, made a suggestion, which is if you have a trapped ion system, then basically what you can do is you can do a 2-photon detuning. So instead of moving to the, so what you do is you typically have a ladder, and then you have a ladder next door, and you can address basically, you can lose phonons this way or this way. And so for instance, instead of losing phonons basically that would make you drop in the ladder by 1, you lose phonons in a way where you drop the ladder by 2. So that would be an A square basically. So these implementations are both in Lee and Sadehpur's paper, but also in my paper, which is cited here. We show exactly how to implement a fairly complex scheme. And so this is one of the kind of typical ways that I would suggest basically.
Okay, great. Thanks. And the second question is from Ricardo. Do you have an example of very dissimilar systems in the classical regime that may synchronize?
I can not off the top of my head, but I can think, because let me just say that you can do fairly bizarre things, like there are these experiments with chemical reactions. There are there are experiments with capacitors and so on and so forth, and all of them are nonlinear oscillators, and many of them put out basically some signatures. So for instance, they change color or they change opacity, which you can easily couple basically. Now, naturally, I don't know. I would have to think, and this is a fair point. But in terms of engineering applications, in terms of engineering non-classical light, for instance, out of these kinds of systems, I think my suggestion is perfectly fair. But I concede that I don't know a good example of an extremely dissimilar classical system that synchronizes right off the top of my head. Perhaps I should. Yeah. So there are two hands raised, I see as well here, Nelly, if there is time.
Yes. So maybe Taufik can go first and then Dominic. Taufik, if you would unmute yourself.
Yes.
You can...
Okay, sorry. Yeah, so my question is, so as I see it, like in the classical regime, when we see like a limit cycle or oscillation, there is an actual like physical observable that is oscillating. But for example, in the example of Bruder, where he defined state 1,0 as a limit cycle, then there's no observable that is like oscillating in that case. So I wonder whether this is a general kind of accepted definition of a limit cycle where there could be no observable that's oscillating, so it doesn't make any difference to any observable. What do it?
I don't understand. Sorry, I don't understand the question, Taufik.
Right. So in the Bruder case, 1,0 is basically state 1,0 is basically
it's a diagonal cycle, limit right? Cycle state. Yes, yes.
In the Husimi-Q representation.
Yes.
So, but if I just stay in state 1,0.
Oh, you're saying what is the free phase there? Which is the question you're asking.
Yeah, the free phase, I can see it in the Husimi-Q representation. But in terms of observable, for example, like momentum or any observable, like Hamilton Hermitian observable, I don't see any oscillating behavior, right? Or
yeah, so the freedom, so the free phase, basically the way it exhibits itself is the fact that it's diagonal. So and so the distribution is diagonal. So if you take any diagonal distribution, this is something that we showed as well in a previous paper. So if you take any, if you take this 3-level atom and you put it in any diagonal distribution, that whole distribution basically has this free phase. And it has several free phases, but it definitely has one free phase. And the free phase is basically the fact that the coherences are not defined yet. And so the absence of the coherence being localized, is the thing that is defined as synchronization. So I agree with you that this is, you might say, this doesn't gel with my classical understanding of synchronization. But yeah, this is the definition. Yeah, you could take a different definition, right? And in fact, this is something that we're writing about. You could take a different definition where you say, I want to see basically, I always want to see something oscillating, and then you either lock them or you don't lock them in the classical or the quantum regime, and this is a perfectly valid point.
Oh, so there exists like a different kind of definition in the literature, or not really?
Not yet. I'm talking about some paper that I'm writing right now, but yeah, not yet. Yes.
Yeah, thank you.
So let me stop myself from making comments. Yeah. So sorry, is it Dominic who had the?
Yes. So Dominic, can you can ask your question, and I think.
Yeah. So related to Taufik, I wonder what is the definition of the limit cycle. Is it the same as stationary state? Is it some solution to some equation?
No. So yeah. So the definition of a limit cycle has to be is the following, which is it has to be such that when you write the state, so you always compute all of these quantities, you compute for steady state, right? So driven or undriven, you start the quantum system, you just let it settle in its steady state, and then you compute whatever you want to compute. So what you do is, in the undriven context, when you take the steady state and you compute the Husimi-Q representation function, the argument is that the same phases that the Hamiltonian moves, right? So this is the example that I had shown before. So maybe I can just go back to this for a second. Can all of you see my screen yet? Sorry, my thing is misbehaving for some reason. So the same phases that basically are moved by the free, yeah, so there it is. So what is the argument here? The argument is that you take the steady state and then you compute the Husimi-Q representation function. There are going to be angles that are determined and there are going to be angles that are free. What angles are free? The angles that are free have to make sense a la classical mechanics. What is that sense? The sense is that the Hamiltonian here is SZ. So the SZ, what is it going to do? Exactly like a pendulum that if I just leave alone, it just has this angle degree of freedom and it just keeps dancing up and down, up and down, up and down. This phase degree of freedom phi just keeps oscillating in a circle. That phase must be free, which means it is unlocked by the bare dynamics. And then you apply a driven dynamics or coupling that locks it. This is the definition.
Okay. May I have a second one?
If possible, can you type your question? Then we can have.
Okay.
We can go into like so that Marty can set up his slides first.
Okay. Can I stop sharing so that Marty can set up his slides?
Yeah, that'll be great. Thanks.
Okay. Take it away, Marty.
So just to thank our speaker.
Thank you. Thank you, everyone.
Very nice.
And I can respond to the questions right here. Yeah.
That'd be great. Yeah. Let's move on in the interest of time to the second speaker.